Hello everyone, I'm Blake Sani, and today I will be walking you through my video lab report for Lab 2, Lines of Charges. The purpose of this lab is to estimate the charge found on a tape strip, this time improving our charge model. In Lab 1, we modeled the tapes as a single point charge, as shown to the right, yielding an approximate charge of negative 1.2 times 10 to the negative 8 coulombs. In this lab, we will more precisely approximate this charge by modeling tapes as a distribution of charges on a line, where the charge was found to be negative 6.5 times 10 to the negative 8 coulombs. The concepts we will be using are Coulomb's law, which relates electric fields and forces with charges at a distance, and distributed charges, which involves the superposition of infinitesimal charges. To replicate this experiment, create a U-tape by quickly pulling a tape strip off of a base tape, shown in Figure 1. Ensure the tape is negatively charged by rubbing a plastic pen and observing repulsion with the tape. Repulsion is necessary because attraction can still occur between a charged and neutral object. Repeat steps 1 and 2, creating 2 total U-tapes. Then, lift one tape under the other until the top tape floats, shown in Figure 2. Finally, record the distance between the tapes for later analysis. To model a line of charges, let's split the tape evenly into n individual charges, each with the charge of the tape's total charge over the number of sections. Like in Lab 1, the electric force on the top tape must fully balance out gravity for the top tape to float, seen in the white and yellow vectors. Also, note that our model becomes more precise as the number of linear charges increases. To trust this model, we need to make the following assumptions. The charge is evenly distributed across both linear tapes. The tapes hold the same total charge. We can use the tape's length to approximate mass. The tapes lie perfectly horizontal, and finally, we can ignore air resistance. From Lab 1, we know that both tapes' lengths are 0.231 meters, tape width is 0.0225 meters, and the distance between the tapes when floating is 0.024 meters. The previous approximated tape charge is negative 1.2 times 10 to the negative 8 coulombs, which was found by solving for charge in Coulomb's law, expressed below. The strategy for calculating the tape charge using our new model, using the GlowScript IDE and VPython, is as follows. Let's first assume the charge from Lab 1 is correct. Then, we iterate over infinitesimal charges to find the net electric force on the top tape. Let's compare the magnitude of this force with that of gravity, and finally adjust the tape charge accordingly so these magnitudes become equal. Using VPython, let's create lines of charge programmatically. The function lineCharge divides a line into n equal sections, each with the properly scaled charge. These lines are also visualized in the rendering. Now, let's calculate and visualize electric fields and forces. For every charge in the top line charge, let's iterate over each charge in the bottom line, summing each electric field for that top charge. Then, sum these net charges for each top charge to find the net electric field on the top tape itself. This is best accomplished by nesting 2 for loops and computing net vectors by leveraging vector addition at every step. Finally, let's adjust the tape charge so that the electric force on the top charge balances out gravity. We can find the proportion of the current electric force magnitude to that of gravity, which is about 18% in this case. Because Coulomb's law has a positive linear relationship between charge and force, we can adjust the tape's charge by dividing it by this proportion. This leads us to find a new adjusted total tape charge of negative 6.5 times 10 to the negative 8 coulombs. Note that these calculations only yield approximations. Still, we can increase the precision of these approximations. As shown, increasing the number of charges on the line increases the precision of our calculated charge. To make an exact calculation, we need the value n to approach infinity. This is difficult for computer environments like GlowScript to accomplish, since they can only sum a series to a certain degree. Instead, to get the exact calculation, we need to transform the series of charges and vectors into an integral, where each small charge q becomes dq, an infinitesimal charge that cannot be numerically expressed. Now, to reflect on this lab, let's ask, what if you had modeled each of your tapes as a single point charge, like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got with your line charge model. Our single point charge model yielded a tape charge of negative 1.2 times 10 to the negative 8 coulombs, compared to negative 6.5 times 10 to the negative 8 coulombs with a line charge model, accounting for a 442% increase in estimated charge. Also, why do these estimates differ? Which value is more likely to be closer to the real value, and why? The line charge model takes into account the distance between every infinitesimal charge, not just the two simplified point charges. So greater charge is needed to span all that distance with an equal electric force. The line charge yields an estimate closer to the real value because it is a more specific, realistic model that makes less dramatic assumptions. Thanks for listening, and I'll be back for Lab 3.